Okay, we are now ready to talk about the second law of thermodynamics. So the second law of thermodynamics says the change in total entropy must increase in the due course of a spontaneous process. Okay, so first of all, what do we mean by this total? Well, often we see in books and even in our textbook that they talk about total entropy as the entropy of the universe. To me, I think this is a little bit misleading because when we think about the entropy of the universe, at least for me, I start thinking about like the Big Bang and galaxies and all that other stuff. When we really want to be thinking about like molecules and chemical reactions. So you often see textbooks call total entropy the entropy of the universe. I just like to call it S total. And total entropy, which again, we could say is the entropy of the universe or whatever, total entropy is the change in entropy of the system plus the change in entropy of the surroundings. And because in thermodynamics, we are free to choose the system and the surroundings however we want, this is where oftentimes I think it's kind of misleading, like we're talking about the entropy of the whole freaking universe, but what we're really talking about is the entropy of like our one little system and its immediate surroundings. Okay. So we remember that capital letters are state functions, hopefully. And the delta means final minus initial. And because this is a state function, what that means is we only care about the final state and the initial state. So we're not looking at like, activation energy, right, that occurs between the final and initial states. We only care about what is the state of entropy at the beginning and what is the state of entropy at the end. Okay, so what that means then is if we think about a positive delta S value, we could say like more disorder or more disorderly. So we've increased the number of microstates relative from the initial state, right? So entropy has increased. A negative delta S, we could say means more orderly or less microstates, okay? Because in a negative entropy, that means the entropy of our final state has to be lower than the entropy of our initial state. So plus delta S, things are becoming a little bit more chaotic, more disorderly. Negative delta S, things are becoming less chaotic or more orderly. And if we look at this second law of thermodynamics, change in total entropy must increase. So that means delta S total, which is the entropy of the system plus the entropy of the surroundings, all together must be greater than zero for a process to be spontaneous. And what's important to note here is not all processes have to be spontaneous. We could have non-spontaneous processes, perfectly fine. And in that case, the total entropy of that process would have to be negative, right? So continuing along, talking about the system and the surroundings, okay? So entropy changes in the surroundings are primarily determined by heat flow. So which way is the heat going? Is it going out or is it coming in? So now if we think about an exothermic process, and I'm going to draw just a little box here, that's my system, and everything outside of this box is the surroundings. So I'll just say SUR for surroundings. So in this exothermic process, heat, which we remember is the letter Q, okay, is leaving the system and going out into the surroundings. So that's going to actually leave the surroundings more disorderly. So when we pump heat out into the surroundings, perhaps, the gas molecules that are in the surroundings will start moving a little bit faster, more chaotically as we increase their temperature, right? So if we have an exothermic process occurring in the system, that leads to more entropy in the surroundings. But what if we have an endothermic process occurring in our system? Well, once again, here's my system. Here's my surroundings. And we recognize that in an endothermic process, heat has to be going in. And because heat is going into the system, it's coming from the surroundings. So that's going to leave the surroundings at a lower entropy state. So again, entropy changes in the surroundings are primarily determined by heat flow from the system. Okay? So if we go back to this equation, our simple Boltzmann equation, right? We remember that from the dimensional analysis, the units were joule per mole per K. And so if we kind of start thinking, well, is there another more general way we could calculate entropy? And there is, okay? So when we look at these units, joule per mole, that has units of heat, which is Q, okay? So I'm going to say delta S. We also recognize that this Q should be reversible so that we can assess what's going on in the system and the surroundings. And by reversible, I mean this, right? That if we play this game, like, okay, what happens if heat goes out? Now what happens if heat goes in? Okay. And then to get that Kelvin unit, we recognize that's going to have to be divided by temperature. So this is kind of like more of a correct version of this Q reversible divided by temperature. But now if we start kind of recognizing, well, where are we going to get that Q from? Aha, it comes from delta H, the enthalpy of a reaction or process. So for example, if we were talking now about the entropy of the system, so I'll write delta S, SYS, okay, we could call that the delta H of the system divided by the temperature of the system, so we can put more specific qualifiers there. But now, what if I want to talk about the entropy of the surroundings? So delta S surroundings. Well, we often are hard pressed to calculate the enthalpy of the surroundings because in chemistry, it's all about the system. So what that means now is because of we see this opposite relationship here, we can say the delta S of the surroundings is negative delta H of the system divided by the temperature of the surroundings. So this gives us a way to think about which direction that heat flow is going. And then we can rewrite our second law of thermodynamics in a way that's going to make it more easy to calculate stuff, which will be the following. So we recognize the entropy of the system is just delta H of the system divided by temperature of the system minus the delta H of the system divided by the temperature of the surroundings. Okay, so we're going to do a sample calculation in the next part of this video.